Welcome everyone. This is episode 9 of the Data Structures and Algorithms course, and today we're going to be talking about algorithm analysis. Now, in order to talk about algorithm analysis, we first have to understand what it is we as computer scientists do. We as computer scientists, when we generate code, I personally ask myself 3 questions. The first one, does the code work? If it doesn't work, then there's no point on giving it out as a final product. The next one, is it easy to understand? Do I have proper documentation? Do I have good valuable names? This is because I am assuming in the future I am giving the code that I developed to someone else so they can look at the code and make adjustments to it. The last one, is the code efficient? If the code is efficient, I am not only saving time, I am also saving resources and compute power, which is very important for me. Now, how do I define efficient? Well, efficient is broken up into three different sections. The first one is the best case, which is denoted by a big omega, and omega is the god of war symbol. The next one is the worst case, which is big O. And the last one is the average case, which is denoted by big theta. I personally am a pessimist, so I assume that every time I run my code, I am going to get the worst code possible, or the worst case for the code to run in. So I look at big O notation. However, these same techniques can be applied to big omega or big theta. So let's go over a simple example. In 2009, a pigeon had a flash drive with 1,000 gigabytes tied to its leg, and it flew all the way over 100 miles to its destination. So, in this case, what is the big O notation? Well, let's get a pen up and running. Well, this is data. On the x-axis, data. And over here we have time. Well, if we think about it, if we had a flash drive of the same size, but it was 2 gigabytes, it would take the same amount of time to transfer it as if it took, so we have 2 gigabytes here. And then if we had 1,000,000 gigabytes, but the flash drive was the same size, it would still take the same amount of time. So in this case, the worst case will be the same amount of time, which would be constant, or big O of n. Nope, it would be big O of 1, constant time. There we go. Now, if we looked at it a different way, so we know that this is going to be constant time, assuming that the flash drive is the same weight. What happens if we have a stable connection and we're transferring data over that connection? So if we had 2 gigabytes per second, well, we can see that that would be linear time, because for 2 gigabytes, it would take 1 second. For 4 gigabytes, it would take 2 seconds, and so on and so forth. However, for the pigeon, whatever the constant time is, it would always be that same time. So let's, instead of talking about pigeons and all this fun stuff, let's go a little more into detail. So there was a good website, I recommend checking it out, that had this picture of big O notation. Now, there are different types of big O notation for O of 1, log n, and so on and so forth. Essentially, we want to stay within this green zone because it would take a certain amount of time. This is okay as well, but we have to worry about really big things that we're running our code on because it'll scale proportionally, and everything else is kind of putting you in the danger zone. We don't really want to be there. Now, let's put some of these into practice. If we were to be given this function here, how would we identify the highest growth of the algorithm? In a sense, the worst case? Well, in order to do this, we would pick the one with the highest, which is in this case n factorial, because that is the highest growing, and it essentially would dominate everything else. There was a way to go about proving this. I'll show this in a different lecture. Now, to move forward a little bit, what happens if you're given code? Well, let's go over some of the examples here. Well, we're starting at position 0, and we're going up the length, and we're going up by 1. So if this had a length of 10, we'd be printing out 10 times. So in this case, it would be n, because if this went up to 100, it would still print out 100. It would be whatever the size of the array is. This is how many times the code will run, assuming n is equal to the length. So now for the next one, we have 3 for loops inside of each other. Let's see what the big O complexity of this would be. Well, we know that the inner one, this is n, and it's being run, again, n times. So that means for each n runs, we are running n times, so that's a multiple. And then one last time for the outer, so n times n times n is equal to n cubed. So this would be the big O notation here. Now the last one, this is a little bit more tricky, but let's go over it together. In this case, we would have this as normal, being n. However, here, we're not going up by 1, we're multiplying it by 2. So if we go back real quick, we can see we have n times going up by I times 2. So it's not going to be n, so it has to be something below it. So it either has to be log n or log 1, because it's not this. However, we are still incrementing by a certain amount, while O of 1 would just be constant. So it's not O of 1. That leaves us with log n. So that means it's n multiplied by log n. And that is how you'd go about doing the big O notation for these, is by breaking it up into smaller sections and multiplying them together. With that, that's all we have time for. I hope you guys have a wonderful day. Thank you for your time.